So welcome. The goal today is, for the first hour anyway, this is the hour 20, we're going to go through 7.3 to 7.5. Then I'm going to take a break, and I'm going to come back and go through 7.6. We're going to talk a little bit more about collisions is where we get to. This is the first midterm results plotted versus the number of hours that you had of sleep the night before the midterm with error bars. So, the interesting trend here is that it goes up. Anybody see anything interesting about this? Anyone want to? What do you think this? What's the meaning? If you're talking right now, talk to me. What do you think is the meaning of this? Beg pardon? Sleep gives you better grades. I don't think I could have summed it up any more succinctly. Thank you. Starting tomorrow, Tuesday, until November 12th, which is the 7th week, we are hoping that you can print and complete this pre-test question. Come on in. Here's the seat. I got chairs here. I have posted this on Quarkus so you can print it off and fill it out and bring it with you to practicals. Here are some thoughts that came in from Learning Catalytics last time. Would the format of the coming test on November 13th, I believe it is, be the same as it was for the first test? Yes, absolutely. Brian and I got together and designed both the midterms kind of in parallel. So we're going to be using those scratch cards again, where you scratch and sniff your answer as you go all your way down and try to find the stars. Same mix where there'll be the multiple choice questions plus a written answer where you have to divide your step into all the solve and evaluate and the simplifying diagram and all that. And same rules for the age sheet and the calculator. Will I post lecture slides? Hopefully you were able to find these under Harlow's lecture slides. It goes over to my private website where I've posted what I think I'm going to do each class versus what I actually did each class, including all the little notes that I write up and anything that I write over on the .cam. So you get to download both if you want. Here's an interesting question. Do you expect us to read the textbook before class? In other words, will you be spending the majority of the class doing difficult problems that require prior knowledge? I think the short answer to this is probably yes. It is up to you and your learning style, but for me, I find reading ahead helps me understand what is going on in classes because I'm not a very good learner by ear. I think I learn a lot better by reading and with my eyes than listening to someone talk. So if it were me, I would definitely read the textbook before I come into class. I do go kind of fast, and like I say, some people are a bit more visual learners, but it is up to you what you think works best for you. Okay. Yes, question?
What sections will the next term test be on?
Yeah, that is a great question. So it's just up to the end of chapter 7, up to the end of the power part. And I think he skipped the Kepler's laws, I think, from chapter 6 is the rumor I've heard. Yes, question? Well, so that's a good question. So did everyone hear that question? I'm going to wait for people to settle down a little bit, and then I'm going to repeat the question. Great question. Is the test cumulative? And I think that the specific answer is no. We will be picking questions from chapters 5, 6, and 7 only, not chapters 1 through 4. But in practice, physics by its nature is cumulative, and so it is good to know some kinematics. It crops up actually in a lot of these problems naturally. And so I think you have to remember what was on chapters 1 through 4, but we won't explicitly be picking questions from those chapters. Okay? Great question. Oh yeah, what's the difference between the change in momentum and the impulse? I don't think there's any difference. I mean, I guess perhaps there's a sort of a philosophical difference that it's force times delta t versus the actual change in momentum, but they're the same, right? Because they're equal. So I would say no difference. This was just answered. And this is a question at the bottom. Does the physics department have a cutoff? I'm trying to get in, so this is more of an undergraduate chair of physics question, which I also happen to be. So no, physics is a type 1 program. It's not restricted. So as long as you've got, as long as you passed everything, then I guess D- would be the cutoff, right? My goodness. Everyone is very active. I don't have this problem in Collin Hall, but I think I'll just mention that it is important for the people around you to be able to hear and focus on what I'm doing. So if you do need to talk, there will be a learning catalytics question coming up really soon, and then we'll take a little break to have a chat. Also, Pius is very diligently setting up a video overflow room if there's people in the aisles. It's probably a bit of a fire code issue to have people sitting in the aisles, but a conservative force. So this is coming up when we do conservation of energy. Sometimes there's this work from external forces, but you don't include the work if it comes from certain external forces such as gravity, because certain conservative forces store work done against them, and they can give back that stored work as kinetic energy. So you actually quantify that stored energy as potential energy. So examples are the gravity and the spring force. And also the electric force. In Physics 132 in January, you will learn about a force called the electric force, which has an electric potential energy, and even an electric potential associated with it in volts, which tells you how much energy is stored in the electric field. And then that produces this force. But so there's a ball. A ball starts here. It goes up. We say that it has gained potential energy, potential to move back down, I guess. So it's moving when it's at this height, and it is stopped when it's at this height. Here's where its energy is mostly kinetic, and here's where its energy is mostly gravitational potential. Same with the spring. If the spring is at equilibrium, it's not moving, or it is moving. If it's moving to the right, it might stretch the spring later and then stop. I can hear my voice echoing off in the next room now. Which means he's probably going to hand me another microphone. Or maybe he's done it somehow. So this is where there's now stored potential energy in the spring. And also if you compress a spring, it can stop it again. And this is, again, stored potential energy in the spring. A non-conservative force just doesn't have that property. Normally it has some source or sink of energy that you can imagine the energy going into or coming out of. For example, if you screech the tires on your car somehow, I don't know if anyone's ever done this, I have not. Has anyone ever screeched the tires on your car? You have? Was it an accident or you were okay? On purpose, okay. Well, there you go. In physics it happens all the time. It's called sliding friction. But in real life, very few people actually screech the tires on their cars. But what it means is that, believe this or not, normally when you're driving, the bottoms of the surface of your tire are not sliding. They're just kind of sitting as it rolls without slipping over the surface. And we'll talk a little more about this in future chapters. But if you're driving along and you go, ah, a cat, and you slam on all four brakes, and then the car goes, and screeches along right before it hits the cat, and the cat keeps walking away, so the cat's okay. Then it looks like this, and you've left a whole bunch of energy on the floor in the terms of, skidding, and you can see the black mark there, and there's all this heat, and all this sound energy obviously is left and broken people's eardrums. Also, if there's an applied force, some people call it F applied, that's a non-conservative force because energy is coming from this person's muscles and going into this object over here. So this force on this person is doing work, external work, which is changing that energy, and it doesn't come from a very easy to quantify potential energy source. Although I suppose there must be chemical potential energy in the muscles of this person. And also an engine in a car, same sort of thing. There's gas in the tank, that chemical energy can get converted into big energy, but we call that a non-conservative force. Imagine you have a cart on a track, one end is raised up somewhat, a cart rolls up, it starts with some initial kinetic energy and speed, V sub I, and then when it gets to the top, it stops momentarily, or it gets further up, it stops. So as it's rolling up, there's a decrease in the kinetic energy. So by conservation of energy, I would like to imagine that that energy that was in kinetic is getting transformed into a different kind of energy. Please make a choice, and I will time you for 1 minute. This is a good time to chat with your friend. Sounds good? We call it gravitational potential energy. I don't have too much to say about this. It sounds like everyone's got it. No? Yes? Let me just say this. The idea with the work done by gravity is that it is path independent. So, for example, I move a book directly sideways, then the work done by gravity is down, the motion is sideways, so there's zero work done by gravity on that path. Then if you go straight down, then the force and the displacement are in the exact same direction, and so it's work equals force times distance. So it's mg is the force times the distance is delta y, the change in y. And since they're in the same directions, there's this positive work mgy. And then if you get down here and move sideways, it's zero work. So mgy is clearly the work done by gravity on this path. It also turns out to be, if you do the integral, the exact same as the work if you go on this path, or any path. And so since work done by gravity is always just dependent on the initial and final height, we can define this potential energy as being negative of that work. And that's what's done in the book. Gravitational potential energy stores the work done against gravity. Delta U equals mg delta y. And this reflects the constant gravitational force near Earth's surface. And when we come back on Wednesday, I'll try to extrapolate to even higher heights if you go way out into space. There's a bit of a different equation, but this is like an approximate equation for when g is constant. Okay, great. So this is another way of looking at free fall. If we just drop a ball off the table, whoops, we can think of it as there's a force on this ball which pulls it down. Or we can think of it in terms of energy, which is this ball has a lot of potential energy. And if it naturally goes down to this height, some of that potential energy will get converted into kinetic. So you can watch it go, because it goes down, well, it even bounced. But as it goes down, there's a conversion of potential energy into kinetic. Oh dear. I have so many wires. I got to be a little less jumpy. Okay. Small mass slides down 4 frictionless slides A through D. And just for the sake of this example, it doesn't really matter, but we're going to say it's the same mass in each case. But they're different shapes, either sort of a shallow straight one, or steep straight one, shallow straight one that starts steep and then goes shallow, or one that starts shallow and goes steep. How would you rank the final speeds of A, B, C, and D when they just hit the ground, just before they hit the ground? Feel free to discuss them. We'll put the 1 minute timer on. 1 once. 1 twice. How's my sound? Sound check? Check, check. So this was a weird one. It doesn't matter. Why? And this really is the beauty of conservation of energy, is that all of the details of the motion don't matter. What happens is you've just got E initial equals E final. And one way of putting that even more explicitly is kinetic energy initial plus the gravitational potential energy initial equals the kinetic energy final plus the gravitational potential energy final. And if you set, this is h equals 0 down here, or y equals 0 at the bottom, then this one final is equal to 0. Okay? And if it starts from V initial is 0 at rest, then this is 0. And so you just get that m times g times h is equal to 1/2 m times V final squared, and that's it. We were just asked about V final. The m's cancel even, so it doesn't even matter if they were all the same mass. What matters is that it's a frictionless slide. And this is really the trick of physics, isn't it? Is that the physics we learn in the playground all has to do with actual friction. And everyone knows that as you slide down a slide, there's a good chance that you won't even slide at all, depending if you're wearing snow pants or if it's rained the day before, all these things, because there's really friction in real life. But it's good to try to imagine what would happen if you were just rolling Hot Wheels cars or something. So good. Here's something to note about the 0 point of potential energy. You can choose it wherever you want. The reason is that only the change in gravitational potential energy has physical significance. So, example, here are two people, Amber and Bill, and they both have meter sticks, but they have defined different 0 points of where y equals 0. Amber does what probably most people would do, is put y equals 0 at the bottom. But Bill, for whatever reason, decides to put y equals 0 at a meter above. Maybe because there's a table there or something, but you can imagine it. This book has 0 potential energy. Unless I push it off like the floor. And then it gains kinetic energy as it goes down. So that's a little weird, right? So which does it have? So here's the rock floating 1 meter above the actual ground. Amber looks at that rock and says the potential energy of that 1 kilogram rock at 1 meter is, I think it's 9.8 joules, if you times it all out. M times 9.8 times 1, right? 1 times 9.8 times 1. Whereas Bill looks at that rock and says, hey, look, that rock has 0 joules of potential energy. They're both right. So how does it work? Obviously, when the rock hits the ground, it destroys your textbook somewhat. So there's going to be a bunch of kinetic energy down here. What Amber says is, well, it started off with positive 9.8 joules of potential energy, ended with 0. So now, just before it hits the ground, it has 9.8 joules of kinetic energy. Bill looks at it and says it started off with 0 joules of potential energy. When it ended up, it had negative 9.8 joules of potential energy. And so, what does that mean? It lost. It went from 0 to negative 9.8, so it lost potential energy, so it gets positive 9.8 joules of kinetic energy just before it hits the ground. And actually, so they get the same physical answer, right? So it doesn't matter. Questions on that? Right, okay, we're good. All right, so now we're moving on to elastic potential energy, a different kind. There's a quick little derivation. The question is, we're going to go back to kind of how we did gravitational potential energy. We talked about the work done by gravity as being mg times the distance. So what's the work done by a spring? Well, this is a problem because it's not constant force. But I can give you the gist of it without doing an integral by saying, look, work equals force times distance, we know that much. Hooke's law for a spring is that the force of the object, which would be the hand in this case, upon the spring is k times x. It's a positive thing now. So that means that it started off at 0 at equilibrium and then got up to a maximum of k times x by the time it pulled out there. Does that make sense? When the spring is not stretched, it doesn't require any force to pull it. But then as it gets more stretchy and stretchier and stretchier, you're pulling more and more and more. So the work, you'd think, would be kx times the distance, so kx squared. But keep in mind that since it started at 0 and increased to kx, it's going to be somewhere between 0 and kx. So the real thing is you do a half in there. Anyway, or you could integrate kx dx, and then there's kx squared over 2 or something. But we're not doing integrals, so just don't even worry about it. Anyway, so the answer is that the work done on the spring is equal to the energy you put into that spring, and so it's U sub s is equal to 1/2 k, where little k now is the spring constant of the spring in newtons per meter, and then x is just how much the spring is stretched, the end of the spring is stretched or compressed away from equilibrium. And what's interesting about this equation is that it doesn't matter if x is negative or if x is positive, you always get positive potential energy in a spring, which is different than gravitational potential energy, which can be positive or negative with an arbitrary 0 point. With U sub s, it's not an arbitrary 0 point, it's very specific. It's 0 when the spring is at equilibrium and not stretched or compressed. It's a physical property of the spring. Whereas it is positive in any other configuration. Okay, so let's get another one of these. Just sending it to your phone right now. So this is a spring-loaded gun. Oh, I know what I didn't do. I didn't do the mousetrap. Here we have, by the way, a loaded mousetrap. And because I talked a little bit about this, is that this has some stored elastic potential energy in one of these springs. And so if you're the mouse and you come over and try to grab the peanut butter, which I think is right here, then all that elastic potential energy gets converted into kinetic energy of all the ping pong balls, flies them all over. But anyway, back to learning catalytics. If you compress the spring by a certain amount, then when the ball shoots out and the spring goes back to equilibrium, then the ball is moving at 4 meters per second. If you take that same spring and same ball and you compress the spring twice as much, so this x has gone to 2x, then at what speed does the ball come out? I guess I'll give you a minute for that. Survey says, oops, wrong thing. So about 50% of people got it. So let me show you how I did it. What I did is I used this, so the basic equation is always that E initial equals E final, right? That's the way I always start these because I just think simply, I guess I have to write something down. It doesn't look like much, but to me that means a lot. So now I just expand the energies into all the energies that I think are important. And the important energies are U of the spring initial plus the kinetic energy of the ball initial equals U of the spring final plus kinetic energy of the ball final. And so this one was, the spring finally goes to 0 in each case, and initially the ball is at rest. So what you say is 1/2 k times x initial, I guess, squared is equal to 1/2 the mass of the ball times v final squared. And so the halves cancel, I guess, and you can take the square root of both sides and try to solve it out. You get something like v final is equal to the square root of m divided by k times just x. Does that make sense? Square roots is what did it to you. So if you double x, you actually just double the speed, even though the energy's gone up by a factor of 4. So that was, if you're thinking E, it is kind of right, like something's gone up by a factor of 4, but it's just the energy. But when you times the kinetic energy by a factor of 4, Which you do, you've only doubled the speed. Okay? So it's tricky. Okay. How are we doing here? So let's do the doc cam note. So we can hit the switch here. So hopefully you can see this. Let me zoom in a little bit. You have a moving car which has 40,000 joules of kinetic energy, and while it's moving at 7 meters per second, could be a little too much information here, a spring-loaded automobile bumper compresses the spring by 0.3 meters when the car hits a wall and stops. What can you learn about the bumper's spring using this information? So this is from the textbook. So what we can do is sketch. We'll do initial. You've got the car with some V initial is 7 meters per second. And then final, and it's got some, I think, uncompressed spring on the front of it somehow. And the final situation is that this spring now compresses and the car stops. And again, I'm terrible at drawing things, but it's not an art class, obviously, else I would get an F. V final is equal to 0, and the spring compresses by some distance x. So the simplifying diagram is something like the kinetic energy initial, which is big, plus the spring energy initial, which is 0, plus, I guess, the work, right, which is 0, is equal to the kinetic energy final, which is 0, plus the spring final, which has got all that same energy. So the idea is just that kinetic energy initial is equal to USF. Okay. Now we could also write this as 1/2 mv final squared equals 1/2 kx final squared. But in fact, they even give you this initial kinetic energy at the top. So K initial just equals 40,000. So we can even just use K initial. What are we trying to do? Let's solve for the spring constant, since that's usually what you would say or learn about a bumper's spring. So if you do Ki is equal to 1/2 little k times x final squared, if you solve it around for k, you get that little k is equal to 2 times initial kinetic energy divided by x final squared is equal to 2 times 4.0 times 10 to the 4 divided by 0.3 squared. And I got 8.9 times 10 to the 5. And the units are newtons per meter as the units of spring constant. So it's just a way of using conservation of energy. And again, I'll post this once I scan it after class. And what's the last form of energy here? Yeah, I wanted to talk a little bit. We'll talk a little more for the next 10 minutes or so, and then also as we get into the second hour, about this work done by kinetic friction. So I'm going to go back to, how do I do? I go like this. So again, I will scan it. Sorry, you're still copying. If an object slides on the surfaces in contact can become warmer. We tried to show this a little bit last time, although it didn't work so well with sliding the bowling ball in the box around on the cart. Where does this come from? Structural changes in the object can occur at a sort of microscopic level when the external force is applied. And so the energy associated with both the temperature and the structure is given by this U internal. And so let's do a quick learning catalytics question on this. Imagine you have a driver who starts the car at speed v sub I, but then the driver puts on the brakes because they see a stop sign and slow down. So initially it has some speed, it's going on a horizontal surface, and then slows down and stops. So I'd like to think, again, that it started with kinetic energy. That kinetic energy just doesn't disappear because of conservation of energy. It must get transformed to a different type of energy. So which do you think it is? Let's do a minute. Okay, so I'm looking at 90%. Any more responses? And stop. And show the results. So yes, it's this internal thermal energy. So that is a little unlike that cart that rolled up the hill and went into gravitational potential energy. In this case, the brake pads in your car are really heating up. And if you just keep, in fact, if you start at the top of a hill and you just drag your brakes all the way down from the top of Whistler down to Vancouver, I mean, you could damage your brakes that way. You can melt your brakes and so. Sometimes they have those. It happens in trucks sometimes. Have you ever seen, if you go on the highway and there's a big down, there's this runaway truck ramp. It's because if so much thermal energy goes into the brake pads of a big heavy truck, it can melt the brakes, and then the brakes don't work, and then you have to go into the runaway truck ramp. So what I want to do is another example, and this will actually show this back on. I'm sure I'm okay for slides. Yeah, we are. So there's that thing we did before, which I'll just leave up there in case you were busy copying that. Okay. A driver slams on the brakes and locks all four wheels, just like you did that one time, sir, but I've never done. And the car skids 18 meters. So I'm not going to do the sound effect, but I really want to. Because as you know, I'm a little full of energy and I'm all wired up, but I don't. I'm trying to be, this is my goal. Okay, so what I did is I watched the video of my class last time when I emptied the video overflow room, and I felt a little embarrassed at just how revved up I got there. And I apologize for that. Anyways, screech, let's just put it that way. And all we know is that the coefficient of kinetic friction between rubber tires and cement is 0.8. How fast was the car initially moving? Now you can imagine this is a very practical problem. What if you are a cop and you arrive at the scene and you see skid marks that are 18 meters long? I'm telling you that even without knowing the mass of the car somehow, unless they should have the mass of the car, we'll see, we'll work it out, you might be able to find out how fast the person was going. So initial situation is that you've got a car. Okay. Oops, again, my artistic skills are terrible. With some V initial, which is, this is the unknown, the question mark. It's going along, and then final. Again, screech. And then it stops. The final equals 0. And so what has happened here is that there's this change in U internal, which is equal to the force of kinetic friction times D, where D, this distance, is equal to 18 meters. And so what you have to do for the simplify and diagram step, there's two diagrams you usually draw in these cases. One is the free body diagram or force diagram for the car, where you have, I guess, the normal force, and you have mg, and you have the kinetic friction. And you have kinetic friction is equal to mu sub k times the normal force. And also, I guess, the acceleration in the y direction is equal to 0. So that means that F net of the world on this car in the y direction is 0. So what that means is the normal force equals mg. Does that make sense? You've probably seen that kind of stuff before. You need that in order to solve the problem, because you're going to need F sub k times d to get that energy that was put in to, I guess, work done by kinetic friction. Do you see that? If I can turn this light up at all. Okay, what are we doing? So, and then the other thing is you can draw these crazy energy diagrams, which is the kinetic energy, initial, plus various things, okay? I guess U sub g is equal to kinetic energy final. And what I do is plus U sub g final, this is initial, plus the U internal. That's converted. So we say that 1/2 m times v initial squared is equal to the F sub k times d, which is equal to mu sub k times n times d. So it's 1/2 m times vi squared is equal to mu sub k times, don't forget what the normal force is, mg times d. Ha ha, I knew it. You don't need the mass of the car. So it's even better. This works for Hummers and smart cars. And then you can solve this out for v sub I. So v sub I is equal to the square root of 2 times mu sub k times g times d. Square root of 2 times 0.8, which is the coefficient of kinetic friction, times 9.8 times 18 meters. And you get that v is equal to, I got 17 meters per second, which I think is around 60 kilometers per hour. Which is okay. It's just sort of normal driving speed, so it sort of works out. It's kind of a long skid, but okay. And just for fun, I have one more. Learning catalytics. Are you ready? A child is sliding down a playground slide at a constant speed. So this is not a frictionless slide. Because if it was, you'd be accelerating down the slide at some g sine theta or something like that. But it's not. It is a friction-full slide. Make sense? And one, not just any old particular friction-full slide, but one in which once you get going, you're sliding down at a constant speed. So while you're moving at constant speed, what is the energy transformation that is going on here? What's being converted into what? So the thing on the left is dropping in magnitude, and the thing on the right is increasing in magnitude. It's transforming. Just 2 minutes. So the one that I like here, personally, is B. And here's my reasoning. It's constant speed. Constant speed. So constant kinetic energy. Ooh, constant, sorry. Yeah. You know what I mean? K. The kinetic energy is neither increasing nor decreasing as you slide down at a constant speed. But something's decreasing. What? being lost as you go down the slide? Gravitational potential energy, very good. So the UG is definitely decreasing. So it's got to go somewhere, so it goes into warming up that child's butt or something like that. So that's it.